Hello everyone. In this video we'll talk about generated clocks. Generated clocks is a topic that has been very regularly asked in the VLSI interviews. So we thought of bringing up this topic over here. So what we'll do is we'll start with a basic divide by 2 circuit. We'll try to build the circuit, we'll try to build the waveform, and then try to create the generated clock definitions out of that particular circuit. Okay, so without wasting any time, let's begin. So we have this particular flip-flop with the D pin. It has got the Q pin and the Q bar pin. And for example, let's say there was a port or a source of clock which was present over here, and that's called the master clock. Okay, so the master clock is present at this point somewhere. That particular master clock is being feeding this particular flop at this clock pin. So now what the proper divide by 2 circuit is getting formed something like this. You have the Q pin, Q port, which is output of this particular flop going to some circuitry, and then you take this Q bar and tie it to the D pin. Okay, so this is your divide by 2 circuit that you will usually see in any of the VLSI circuits. This is a very common divide by 2 circuit. So let's see how does this function as a divide by 2 first of all. So let's say this is the output of this particular thing is a generated clock. We have kept a short form over here, which is called as gen underscore clock. So now if you look into the waveforms, we'll try to understand this circuit in terms of waveforms, and then we'll try to create the generated clock at this point. Okay, so the waveform, let's say this was the master clock. A master clock has got a 50% duty cycle. It is at the leading edge for 50% and at the trailing edge for 50% of the clock, and this is your clock period. So clock period is from this point to this point. Okay, and now let's bring up the other nodes. So for example, Q, which is this is the point where you have defined the gen clock. Initially, let's assume some initial condition, and in this case we are assuming the initial value of Q is 0. That is, initial gen clock value is 0. Okay, so if Q is 0, your Q bar is 1. If your Q bar is 1, your Q bar is being fed to the D pin, so your D pin is 1. So these are the initial conditions we have to understand. And in the different way, you can take the Q as 1 and hence derive the similar kind of waveforms with respect to whatever initial conditions you want to put. You can always do that, but for the sake of simplicity, we have taken this as initial conditions. So 0, the Q is 0, Q bar is 1, and Q bar is being fed to D, so D is also 1. So now during the first clock edge of the master, so this is a rising edge flip-flop. So during the first clock edge of this particular master clock, your D will be pushed to Q. Your D, the data that is present at the D, that will get pushed to Q. Okay, and Q bar is a reverse of Q. So the waveform will be something like this. So the D is logic 1. Q switches from logic 0 to logic 1, which is nothing but the D. So D is pushed to Q. Okay, Q bar will be exactly opposite to Q, so it will switch to 0. It will switch from 1 to 0, and since Q bar is being fed to D, your D is switching to 0 from logic 1 to logic 0. Okay, now during the next clock cycle, when the next clock cycle of the master arrives over here, at this point of time, your D which is at logic 0 will now get pushed to Q. So Q, which is at logic 1, will now go from logic 1 to logic 0, something like this, because the D is 0. So D gets pushed to Q, and the output is logic 1 to logic 0. Okay, so since Q bar is a reverse of Q, so it will rise from logic 0 to logic 1, something like this. And similarly, since Q bar is being fed to D will rise from logic 1 to logic 0. Sorry, logic 0 to logic 1. So moving on, if we try to implement this circuit even more further, so the waveform will look something like this. So your D, which is now logic 1, in the next clock cycle will be pushed to Q. So now your D, which was logic 1, is pushed to Q. So Q moves from logic 0 to logic 1. Okay, Q bar inverse of Q will go from logic 1 to logic 0, something like this. And since Q bar is being fed to D, your D is also switches from logic 1 to logic 0. And similar for the next clock cycle also. So this even you can derive your Q moves from logic 1 to logic 0 because your D is 0. D is getting pushed to Q. Okay, and similarly Q bar and D switch respectively. So this is the waveform. Now for a static timing analysis tool, this waveform that you get at the gen clock, let's put this waveform over here. So this waveform that you get at this particular point of time, okay, the further circuits which will be connected to this particular gen clock, which are this particular flops, has to be characterized with this waveform and not this waveform. So this is the waveform which is being fed from external world. So we create this clock, we create this as a master clock, and the output of this particular clock, which is generated clock, we create it separately because this is a static timing analysis tool. It's not a dynamic timing analysis. So basically whatever waveform you achieve at this point of time, that has to be defined somewhere so that the further analysis will be done based on this waveform. Had it been a dynamic circuit, in this case this particular waveform would have been automatically derived at this point. But since it's a static timing analysis, it's a static timing analysis tool, so this particular gen clock, what we get at the output after understanding this particular circuitry behavior based on these graphs, you need to get this graph at the output of gen clock, and the further circuit has to be analyzed with respect to this waveform. So we have to construct this waveform, or you have to code this waveform in such a fashion. There are some syntax and semantics to it. So you have to code this particular waveform in a syntactical manner so that the following circuits will understand this particular waveform. So how do we do this? So we have got a special tool. It's called as a generated clock. Basically, if we have got a special setting that is called as generated clock, we can create a generated clock at this point of time, which is derived from this particular master clock, because on a functionality base, the generated clock is derived from the master clock. So we can code this particular functionality in this format. So for example, generated clock has got certain properties. It has got the name, it has got the source name. So name is basically the name that we try to give to this particular new clock that is getting derived at the output, and we call it as, let's say we call it as gen clock. Okay, the source name or the pin and the port name, so it says that what is the source of this particular generated clock. In this case, the source of this particular generated clock is nothing but the master clock. So we put the master clock table value over here. Okay, now what else can we see? We see that this output waveform is a divided by 2 of the master clock waveform. So for example, if this was the clock period of the master clock, let's say this was 1 nanosecond, and 1 nanosecond is equivalent to 1 gigahertz. So now this particular waveform is like 2 nanoseconds. So 2 nanoseconds is 500 megahertz. So this clock is getting divided by 2. So that's why if you see, there is one more option that you see over here, it's divided by 2. We put a value over here, it's called divided by 2. Okay, and duty cycle, we don't put a duty cycle over here because this is being derived from the master clock itself, and since it's a divided by 2, there is not much control over the duty cycle. So duty cycle is valid only for a multiply by circuit. So we'll be looking into the duty cycle thing much in some other videos. Basically the next videos or the upcoming videos will be looking into duty cycle also. Okay, and rest all the other options that you see, so those are not valid for this kind of waveform. So for example, you have a multiply by option, but this waveform is not a multiplied waveform, it's a divided by waveform. So you keep it as you keep it as blank, or you put a dash over here. And this waveform is not an inverted waveform, it's a straight waveform. So again you put a dash over here. And there are 2 more options, which is edge and shifted edge. So I'll be talking about edge and shifted edge kind of waveforms in the later videos. So for this particular waveform, for this particular video, let's keep it as dash. Okay, so this basically represent your generated clock. So whenever we are asked about generated clock or deriving a constraint for generated clock, this is the table that you need to fill. Once you fill up this table, the constraint for the generated clock will automatically get derived. Okay, so this is the basic table a basic table for it. So what we'll do is, since this was a very simple circuit, it was a very basic divide by 2 circuit, we'll look into more complex circuit and more complex waveform and try to obtain the generated clock properties and try to fill up this particular table. So let's try to look into a more complex waveform in the next video. Thank you.